Now, this example is for the inclusion which is formed during the MnSi deoxidation process. In the most of the time, we are adding aluminum to remove the oxygen in the steel, and then you can produce the Al2O3 alumina inclusion. And sometimes this kind of alumina inclusion is very bad for the steel quality, especially as you can see here for the tire cord steel or very thin inbar steel. If you have the alumina inclusion, that alumina inclusion can be the crack initiation site. So we want to avoid this kind of the solid and very hard solid alumina inclusion particle. So one of the technology we can use actually to avoid this kind of alumina inclusion is the MnSi deoxidation process. And through this MnSi deoxidation, we can reduce the oxygen to the certain range, but this actually certain range is the higher than actually the aluminum deoxidation. However, while we're actually making this kind of while we are reducing the oxygen content, we can make MnOSiO2 and MnOSiO2 and Al2O3 type of the inclusion. And those inclusions sometimes can be the liquid state, even at around 1200 degrees Celsius or even below that temperature. And they can be, they can have the less actually harmful effect for this kind of crack actually formation. So for some special steel grade, people used MnSi deoxidation technology than the aluminum deoxidation technology to remove the oxygen content. This is the phase diagram for the MnOSiO2 Al2O3 ternary system. And this diagram tells you why people developed the MnSi deoxidation technology. So, for example, if you make alumina inclusion, the melting temperature of alumina is above 2000 degrees. Okay, and SiO2 is also about 1700 degrees, and MnO is also 1800 degrees Celsius. When Mn and Si form the solution, Mn and Si actually form together, sorry, and it can make Mn2SiO4 and MnSiO3, and then some liquid phase in the middle. And if you look at all this phase diagram, isothermal actually line here 1800 degrees, 17, 16, 15, 14, and 1300 degree, and then there's another 1300 degree. So within this range, you can see that there's the possible liquid inclusion which have the melting temperature down to about 1250 degrees Celsius. Okay, and then if you add a little bit of the alumina into this system, now you can see the isothermal line for the 1200 degrees Celsius, even at 1150 degrees Celsius. Okay, so if you actually make your final inclusion composition within this range, you can make liquid inclusion. You can keep the liquid inclusion even at 1200 degrees Celsius still process. Okay, so this is the main reason why people was interested about MnSi deoxidation. So instead of the solid alumina inclusion, you can make a liquid inclusion, which is more suitable for those special alloy application. Okay. Then MnSi, why we are not just looking at the MnSi binary phase diagram? Because while you are doing the steel making process, aluminum can be coming as impurity from the many different sources. For example, even when you do this kind of the MnSi deoxidation, you have to use the ferroalloys like ferrosilicon and the ferromanganese. And this kind of the alloy, you have sometimes very small amount of the aluminum as an impurity in the ferroalloys. And those kinds of small impurity aluminum content already make alumina inclusion because aluminum has a very strong affinity with oxygen. So even you have about 10 ppm of the aluminum in the liquid steel, it can generate a lot of the alumina inclusion. Okay, so that's why aluminum oxide is very difficult to avoid. So if you actually have the MnSi deoxidation, you can have this kind of inclusion in the beginning, But while you are reacting with the aluminum in the steel, you can move that inclusion chemistry to this target chemistry range. Then you are safe. And of course, in the real actual steel making process, we are not just doing inclusion formation like this. And while we are actually doing the ladle furnace process or any other special actually refining treatment, we can even further modify this kind of the inclusion by reacting with the top slag. So we can even change this actual chemistry from the MnOAl2O3SiO2 system to the MnOSiO2Al2O3 with the CaO and with a little bit of the MgO actually containing system. And by doing so, we can even find better inclusion composition, which have the even lower melting temperature than 1200 degrees Celsius. So this diagram show you what we want to actually calculate in this example. So this is not done by only phase diagram calculation. So we did two kinds of the calculation here. The first one is we did phase diagram MnOSiO2Al2O3 ternary phase diagram calculation. And then after that, we did the equilibrium calculation to calculate the inclusion chemistry change depending on our Mn and Si ratio. Okay, and then once we get it, we just superimpose those actually the result from the equilibrium calculation and put it into the phase diagram, and then draw this kind of the line to show the trajectory of the inclusion depending on the Mn and Si ratio, and then with the increasing of the aluminum concentration in the steel. So we want to do this kind of the calculation in this example. To generate this kind of the inclusion trajectory phase diagram, the first thing is we have to calculate phase diagram over the MnOAl2O3 SiO2 system. So let's do the calculation of the ternary phase diagram. But as I mentioned before, manganese actually have manganese 2 plus and 3 plus cation state. So we have the multiple actual oxidation of the manganese considered in our oxide database. So if you simply use the MnOAl2O3 SiO2 as a component and then try to do the phase diagram calculation, then FactSage sometimes cannot calculate your phase diagram. So here I intentionally add oxygen to make a reducing partial pressure of oxygen and then try to draw the MnOAl2O3 SiO2 phase diagram. Okay, so you enter MnOAl2O3 SiO2 and then add one more oxygen here, and then the unit is temperature and gram Celsius and the gram in the weight unit. And then you go to the database selection, and we are taking FT oxide database and the FACT PS database because we are fixing the partial pressure of oxygen. And then say OK, and then go next. And then you can select all solution phase and then all solid phase as well. Okay, you don't have to select the gas phase because we only pick the partial pressure of oxygen as a constant value instead of giving the amount of the oxygen. Okay, so that's good. And then you go to the variable, click the mouse, do the mouse left click, and then you can have the triangle diagram A, B, C, and then number of the composition you want to change is 2, and number of the activity you want to change is 1. This will be partial pressure of oxygen. And then next, the temperature 1600 degrees Celsius, and then what you want to make this partial pressure activity value here, O2, and then gas state 10 to the minus 12, and this should be reasonably reducing condition at this 1600 degrees Celsius. Okay, and then we set the A, B, C corner of the given triangle diagram. A corner I set SiO2, B would be MnO, and then C corner would be Al2O3, as we've seen in the previous phase diagram. And then we can say OK, and then to calculate. Then you have phase diagram is the calculating in this figure here. So it is all done, and then if you go click, now you have slag phase here, and this is monoxide plus slag. So in this case, monoxide is MnO, and then you have some mullite, and you also have the alumina. Corundum is alumina in this case, and then you have spinel plus slag, and here you have SiO2 plus slag. Okay, so it is done. Even, for example, if you want to see, okay, so whether this slag is really reducing condition or not, Mn2 plus is major one or not, you can even go, for example, phase equilibrium mode, and then click one of the composition, say okay, and then check your composition. So manganese is 40.3, and the Mn2O3 is almost nearly 0. So it's quite reducing condition. So it's effectively same as the MnO, Al2O3, SiO2 ternary system. That's okay. So now I will save this one first. Save as. So I will say this is MnO, Al2O3, SiO2 at 1600 degrees Celsius. Okay, so we save this figure for later actually and then later when we calculate the trajectory for the inclusion, then we'll plot it on top of this phase diagram. Okay, so now let's close it. And then the next one is now equilibrium calculation. So here, now I open the equilibrium program. I already also set up the composition for the Mn and Si and the aluminum and oxygen here. So I want to do the calculation for the inclusion at when Mn and Si ratio equal to 1, and when Mn Si together will be 1, 1.0 composition. So 0.5, 0.5 Mn and Si in weight percent. And then I'm adding certain amount of oxygen. So in this case, about 70 ppm of the oxygen. And then I'm changing the A variable for the aluminum concentration. And then the rest of them is iron. Okay. So if you are not adding any aluminum, it will produce only MnO SiO2 type of the inclusion. But when you add small amount of aluminum, so it's basically the modification of the inclusion by the small impurity of the aluminum in the liquid steel, and that will change the MnO SiO2 inclusion to the MnO SiO2 Al2O3 inclusion in the end. So I'll change this A from 0 to the certain value to see the change of that inclusion chemistry. And the unit is temperature in Celsius, in the quantity in gram, and then the database here, I want to select the FT oxide database because the inclusion will be FT oxide. And then liquid steel you have to select, and you can select either FS steel database or FT FeLQ from the FT miscellaneous database. And in this case, it's a very dilute condition, and we are looking for the very precise inclusion calculation in low carbon steel, almost pure iron. So I'll take a FT miscellaneous database in this case. Then, so now we select the liquid iron database from FT miscellaneous, and then we select all the rest of the solution from the FT oxide database. And then we also select all the possible solid phase, and temperature is 600 degrees Celsius. And then we set actually A variable here, the variation of the aluminum from 0 to 0.005, it's 50 ppm, and every 1 ppm. So we'll do 51 calculation. Okay, it's a very small quantity as you can see. And then let's run the calculation. If you run the calculation, you get the result like this. So let's check couple of calculation. So when A equal to 0.0005, so it's 5 ppm, then we have liquid steel. And if you look at the composition of liquid steel, we have 0.49885% of manganese, and then even silicon is almost 0.49 and etc. And theoretically, instead of reading this one, you had better read this one for the composition. So if you want to read this one more precisely, we have almost 0.5% manganese, almost 0.5% silicon. So the composition of our steel is maintained 0.5 manganese, 0.5 silicon. And then you can see that aluminum amount is about 1.2 ppm because it's a mass fraction. So it's 10 to the minus 6 is the 1 ppm. So it's 1.2 ppm. And oxygen amount is 53 ppm in this case. And then so that we add 5 ppm of the oxygen, we remain only 1.2 ppm of the oxygen. So it means about 3.8 ppm of aluminum was used for something else. So here we have this amount of slag is forming. So about 10 to the minus 3 in the 100 grams. So it means about 39 ppm of the liquid inclusion is forming. And the liquid inclusion is mainly MnO, SiO2, Al2O3. So you already see that alumina in the inclusion is about 18% with 1.2 ppm of the aluminum in equilibrium in the steel. Okay, so it's a very small amount of the aluminum already generate quite significant amount of the alumina in the inclusion. Okay, and the rest of them is all zero. So you can check one by one like this, but I think this is enough for checking. And then we can go. And also one thing I want to mention is because our condition for the calculation was the Mn and Si ratio equal to 1 to 1, and then together will be 0 to 1%. Okay, 0.5, 0.5. So you had better set your initial condition here. So especially the oxygen amount and aluminum amount to make sure that you can maintain your original steel composition like this. Otherwise, your calculation is deviating from your original assumption. Okay, so you have to make sure this kind of the content. Okay, now I wanna take out this liquid inclusion composition, for example. Then we can go to the output and select save or print as, and then I'll take as an Excel file. I'll take out the information in Excel file, Excel spreadsheet setup. We say, this one, we don't need anything special here, but we can simply say alpha, okay, depending on the initial amount of the aluminum, how is it going to change alpha? And then we set up here weight percent of the Al2O3, for example. And then if you like, you can also include some gram of some other pages to actually see the total inclusion composition. But in this case, I want to just do the very simple calculation to see only liquid inclusion composition. Okay, and if you want to see the overall inclusion composition, you can see the pyrometallurgy and the Paris application number 2. That slide show you how to sum up overall composition of the inclusion, and then you can do the plot of those things in your inclusion diagram later. Okay, but in this case, I'll simply show you how to plot only liquid inclusion composition. Okay, so weight percent, and then select now. I'll select the weight percent of all the liquid inclusion composition. So if you go down here, the slag, I want to take this slag composition. That's what I want to do. And then say OK, and then OK, and then OK, and then you can say open, and we'll see the result of this liquid inclusion. Okay, here I have Excel file. So you can see that this is FeO in the slag. So this is liquid inclusion, Fe2O3, MnO, Mn2O3, Al2O3. And then you can see Mn2O3, and then there's another SiO2, etc. So this is slag number 1, slag number 2. And we don't need slag number 2 at the moment, so I'll just delete all of them because there's only slag number 1 existing in this case. So now I have to set the axis. Okay, so top was the top of the diagram we draw was SiO2, and then left side. So B corner was the MNO, and then right side was Al2O3. You can take only these three components from this calculated result, or you can sum up some other thing together to redefine your the three corner. I'll take SiO2 as a pure SiO2 as it is. Okay, so this one. And then I'll take Al2O3 only from the Al2O3 if you like. Or if you want to, you can take it also Mn2O3 if you like into the Al2O3 and Fe2O3 also into the Al2O3. But it's up to you. But if you do this one, then you can basically say 100 minus this one, or you can sum up all the rest. That will be the MNO, kind of normalized MNO amount. Okay, and then you can let's just go here. You can simply click this way, so you can have all the result. But you have to be careful here, and you cannot actually plot this result directly because in the fact stage, in the diagram you draw, so for example, this diagram you draw, this is all in the mass fraction. So you have to make sure that sum of the three together will be 1 in this case. Okay, so if you go back to the Excel file, instead of this way, you have to say divide by 100. And then same thing, divided by 100. And then this will be 10, 1 minus this one minus this one. Okay, so that's better. And then say okay. And then you can do the control C. Okay, copy all these three axes, A, B, C axis. And then you can go to your phase diagram. And then you can plot it here. So you can add, so you can control V. Sometimes control V is not working. Then you can even do the edit, edit, and then paste. And then paste as a line, for example. Say okay. What kind of line? Thick line with red color, for example. Let's see how does it look. You see. So this is the completion of my liquid inclusion. Okay. So this is a little bit strange. How come I have liquid inclusion here? But certainly this area is the liquid inclusion. And then if you probably connect all the remaining solid actually inclusion together, then this trajectory will go to the alumina eventually. So this is Mn-Si ratio 1 to 1, 0.5, 0.5. And you can do the similar calculation for the 1 to 2 and 2 to 1 and 1 by 1 like this. And if you draw it 1 by 1, you'll see the trajectory of the inclusion depending on the Mn-Si ratio in this case. Okay, so this is good. And let's just close it. And then sometimes, for example, you did this inclusion calculation in Excel Equili program. You might say that, oh, I like this calculation. I want to use this calculation in the future again. Then you can save this result, save the file, and for the entire system. So for example, you can go save or save as, and you have to know which directory are you using. Then let's say save, and then I can save this one as MnSi deoxidation, and then by default the name is Iki. Then say the extension is Iki, and then this is MnSi at 1600 degrees Celsius, for example. So I save it like this. So whenever in the future, if you do something else, so you do a lot of the other calculation, and then you feel like suddenly, okay, I want to actually see that calculation result again. I have to change a little bit of those calculation and run some other simulation, for example. Then you can simply come back to the file, open, or you can simply go here, open, and then you can find out the list of the saved file by yourself. And then here, I think this is the one I just saved it. Okay, MnSi deoxidation. If you open it, yes. Then all the phase selection, all the composition database selection, phase selection, even the final condition is stored as it was. Okay, so simply you can just click again to run the calculation, or you can simply just go and change a little bit of this condition without touching anything else, and then you can run the another calculation. Okay, so in this way you can build up a lot of the example like this for the complex actual example and save it as a file, and then whenever you need it you can just simply go and open it and run the calculation again. So I have a friend actually who is utilizing this kind of the saved file a lot, because in reality if you are working in the certain industry, you need probably, let's say, about 10 to 20 calculation like this, and you can simply change some of the number, then you can actually more or less actually uh, the more or less actually the cover the most of the you actually the calculation you need in for your job. So in that case, you can keep saving the file like this, and you can do the same thing in the in the phase diagram program as well. Okay, so this is a little bit tip for you to keep it. And also, if you actually have the problem, and then basically you can simply send that equi file to me, then I can open it and see it, what kind of the mistake or what kind of recommendation I can actually add on those kinds of equi file, and then save that actual file and then send it back to you. Then you can simply open like this and then check what kind of modification is necessary and what kind of thing is done, and then you can run the calculation continuously. Okay, so this is the way we can do the communication through this equi file. Okay, that's good enough. So if you have any further question, you can also contact me anytime. Thank you very much.